Hello everyone, good afternoon. This is Group 109 and we're presenting leveraging CNNs for precision defect localization and silicon wafer production. My name is Vandya and my teammates are Ankit and Rohan. Coming to our motivation, semiconductor chips are the backbone of modern electronics and key to technological advances. Their manufacturing involves highly sensitive processes like oxidation and photolithography, where even a minor defect can reduce chip yield and performance. As devices become smaller and denser, defect localization becomes critical. Our goal was to develop a CNN-based classifier which aims to accurately locate and categorize these defects in order to support quality control and process optimization. Dataset overview. So our dataset is from the MIR W811K dataset. This dataset contains over 800,000 images of silicon wafer defects, and they have key features. Out of these, the notable among them are the failure type, the train test label, and the wafer map. The failure type has the defect classes, which are of 9 and which can be seen in the image seen on the left. And the train test label helps in categorizing the data to training and testing. And finally, we have the wafer map, which consists of the core image data. Coming to our methodology, our input are the raw images from the 9 defect classes, which have non-uniform resolution. This goes to the data preprocessing stage. Here, our images are resized to 64 cross 64 pixel resolution, and they are balanced with over 100 samples per defect type. Next, we have the train test split. Here, the data set is split with 80% reserved for training and the other 20% will be for testing. And finally, we are passing this data to our model architecture, which comprises of a CNN with 2 convolution blocks and dense layers, which is used for multi-class classification. And finally, we have the optimization strategy. Here, we use class weights and train with Adam and categorical cross entropy. Finally, our output will be the predicted labels of 9 defect classes. So coming to our data pre-processing stage, here our raw colored images from the dataset are loaded from the folders and they are resized into 64 cross 64 pixel. Next, we have the label assignment. So each defect type is mapped to an integer label from 0 to 8. On our right, we have the 64 cross 64 pixel resolution images with the label type. And finally, we have the balance check. In order to ensure balanced training, we sample exactly 100 images per class. And finally, our output will be the pre-processed images with the corresponding labels, and they are stored as NumPy arrays, which are ready for training. Moving on to our baseline CNN architecture, we have the architecture divided into 3 stages: the feature extraction, classification, and the optimization. The feature extraction has 2 convolutional blocks. The first block has 32 filters, which detects edges or simple patterns. Next, we have the second block with over 64 filters, which identifies complex shapes. And finally, the max pooling layer, which condenses key features in order to see the defects clearly. The classification layer helps in flattening the output and passes it on to the dense layer with 128 neurons, followed by a softmax output layer that predicts one of the 9 defect classes. Finally, we have the optimization. Here we are using the categorical cross entropy as our loss function. This is well suited for multiple classification problems. It penalizes incorrect predictions based on the confidence of the wrong class. Our optimizer is Adam, which auto adjusts learning speed in order for efficiency. Our model evaluation and performance summary. We have the classification report, which shows how classes like donut and near full are having a perfect recall, while classes like scratch are underperforming. This shows that we can use augmentation or simple balancing in order to improve our model more. Then we have the metrics. So this metrics is for our validation test data. Here we achieved an accuracy of around 85.4% with a precision of 86%, a recall of 86, and an F1 score of 85%. We have the graph for the training and validation accuracy. Here we see that the training accuracy is reaching over 95%, and the validation accuracy is reaching over 86%, and they're stabilizing after 10-15 epochs. The same goes for the training and validation losses. So what we can conclude from this is that no severe overfitting is observed. So this is our confusion matrix. And as you can see, some classes are performing well, while classes with complex patterns are not performing that well. So this is just a comparison of our previous model and our current model. So earlier we were using grayscale images, but now we are using RGB images with 64 cross 64 resolution, so that the CNN model can detect the features more clearly and preserve it. So our evaluation also includes a classification report. Prior work, none of our teammates had any direct experience, and this is our first project, and we have had a very fruitful approach in doing this project. These are our references. Thank you. Have a great day.